These are the temperatures that make Antarctica look like a warm afternoon, the numbers that separate the coldest place ever measured on Earth from the emptiness that fills almost all of the universe, and the reason the coldest spot we know of was not found by a telescope at all, but built by hand inside a laboratory. This video covers what cold actually means once you leave the atmosphere, how close to absolute zero nature and human engineers have actually gotten, and what happens to a spacecraft, a nebula, or a single atom when there is almost no heat left to lose. If any of that sounds like the kind of thing you want more of, go ahead and hit like and subscribe before we get into it, because we cover stories like this one every week. Let's start with the basics, because the word cold gets used so casually in everyday conversation that it's easy to forget what it actually means at the level of physics. Temperature, in the simplest possible terms, is a measure of motion. Every atom and every molecule in a substance is jiggling, vibrating, or moving around to some degree, and temperature is essentially a way of describing how much of that motion is happening on average across a huge number of particles at once. A hot cup of coffee has water molecules bouncing around rapidly, colliding with each other constantly, transferring energy back and forth in a chaotic blur. A block of ice, by comparison, has molecules locked into a rigid structure, barely able to move at all, vibrating only slightly in place, like dancers frozen mid-step. Cold, in other words, is not a substance that gets poured into an object, the way water fills a glass. Cold is simply what's left over once heat, in the form of that underlying motion, has been reduced or removed. That distinction matters enormously once you start thinking seriously about deep space, because it means cold isn't a fog that drifts through the vacuum between stars and settles onto anything unlucky enough to be sitting out there. There's no cold cloud floating through the galaxy waiting to seep into a spacecraft's hull. Cold is what's left behind after heat departs. Or in the case of most of the universe, cold is simply what things look like when there was never very much heat there to begin with. And that raises an obvious follow-up question, one that sounds almost childishly simple, but turns out to be one of the deepest questions in all of physics. How far can that removal of motion actually go? Is there a floor, a hard bottom limit beneath which nothing, anywhere, under any circumstances, can ever fall? It turns out there is, and it has a name, and it has an exact number attached to it. That number is 0 Kelvin. 0 Kelvin is equal to about -273.15 degrees Celsius, or -459.67 degrees Fahrenheit, and it's known throughout physics as absolute zero. In theory, absolute zero represents the point at which all molecular motion would come to a complete and total stop. No vibration, no jostling, no residual jiggling of atoms whatsoever. The coldest that matter could conceivably ever be, an ultimate floor with nothing beneath it. But here is the strange, almost unsettling thing about absolute zero. Nothing, anywhere, in the entire history of scientific measurement, has ever actually reached it. Not in a laboratory, not out in the depths of interstellar space, not anywhere that instruments have ever been able to detect. And crucially, this isn't simply a case of our equipment not being sensitive enough yet, or our engineering not being clever enough yet, waiting patiently for some future breakthrough to finally close the gap. It appears, as far as physicists currently understand it, to be genuinely, fundamentally impossible, and that impossibility is written directly into one of the oldest and most rigorously tested laws in all of thermodynamics. That law is called the third law of thermodynamics, and it was first formally stated back in 1912, more than a century ago now, long before anyone had built a spacecraft, launched a satellite, or even dreamed of photographing a nebula in enough detail to measure its temperature from thousands of light years away. In plain, everyday language, the third law says something like this. As you cool a system down closer and closer toward absolute zero, each additional increment of cooling becomes progressively harder to achieve than the one before it, to the point where reaching absolute zero exactly, precisely, completely would require an infinite number of individual cooling steps, each one smaller than the last, stretching on forever, without ever quite arriving. Siabal Mitra, a physics professor at Missouri State University, summarized this idea about as clearly as it can be summarized. One version of the third law states that it would require an infinite number of steps to reach absolute zero, which means you will never get there. You can always get colder than you currently are. You can always shave off another fraction of a degree, and then another fraction after that, and another after that, getting closer and closer to the line with every attempt, but never quite touching it, no matter how many attempts you make or how sophisticated your equipment becomes. There's an old philosophical puzzle attributed to the ancient Greek thinker Zeno about a person trying to cross a room who can only ever cover half of the remaining distance with each step they take. Take one step and you've covered half the distance to the far wall. Take another step and you've covered half of what remained after that first step. Keep going forever, taking smaller and smaller steps, and in principle, you get closer and closer to the wall without ever technically touching it, because there's always another half distance left to cover, no matter how tiny it becomes. Absolute zero works in a strikingly similar way, except the room being crossed isn't physical distance at all. It's temperature itself, and the wall you're approaching, but never quite reaching, is a mathematical, physical limit built directly into the structure of the universe. You can get remarkably close. As we're about to see, human beings have gotten astonishingly, almost unbelievably close. But the wall itself, the true 0 point, remains permanently, structurally, unreachable. So if absolute zero can genuinely never be reached, no matter how advanced our tools become, the real and far more interesting question becomes, how close has anyone, or anything, natural or artificial, actually managed to get to that unreachable line? And the answer, which we're going to spend the rest of this video carefully unpacking, piece by piece, contains a twist that runs directly against what most people would probably guess without thinking too hard about it. The coldest known conditions anywhere in the entire universe were not discovered out among the stars, drifting through the emptiness between galaxies. They were built, deliberately, painstakingly, one careful adjustment at a time, inside laboratories right here on the surface of planet Earth. But before we get to that twist, and before that twist can make any real sense, we first need to understand what cold actually means once you leave Earth's atmosphere behind entirely, because deep space behaves in ways that break a surprising number of our everyday, ground-level intuitions about how temperature is supposed to work. Before we go any further, it's worth pausing on where that number, 0 Kelvin, actually came from in the first place, because the story behind the Kelvin scale itself is almost as interesting as the physics it describes. The scale is named after William Thomson, who later became Lord Kelvin, 1st Baron Kelvin, after his elevation to the nobility in 1892. He was born in Belfast, Ireland, on June 26, 1824, and his family later moved to Glasgow, Scotland, where his father took a position as a mathematics professor at the university there. Thomson turned out to be an extraordinarily precocious student, enrolling in university classes at the age of just 10 years old, and by the time he was 21, he had already studied in Glasgow, in Cambridge, and in Paris, and had published a dozen scientific papers of his own. In 1846, at just 22 years old, Thomson was offered a professorship of natural philosophy back at Glasgow, where he went on to establish the first physics laboratory anywhere in Great Britain, and where he would go on to spend the rest of his career, more than 50 years in total, even as his growing reputation drew international attention. In 1848, Thomson published a paper with a long, formal title, On an Absolute Thermometric Scale, founded on Carnot's theory of the motive power of heat, and calculated from Regnier's observations. And inside that paper, he proposed something genuinely novel, a temperature scale that wouldn't depend on the specific physical properties of any one particular substance, the way earlier thermometers often did. Instead, his scale would be built around a single fixed, absolute reference point, a true zero, the coldest temperature that could theoretically ever exist, the point at which a gas's volume would mathematically shrink down to nothing at all. Thomson calculated that this absolute 0 point sat at around -273 degrees Celsius, remarkably close to the modern, far more precisely measured value of -273.15 degrees Celsius that we still use today. Later in his career, Thomson also helped formulate a version of the second law of thermodynamics, and he co-discovered what's now called the Joule-Thomson effect, which describes how the temperature of a gas drops as it expands from high pressure into low pressure. The exact same underlying principle, incidentally, behind why an aerosol can feel cold in your hand right after use, and behind the very same refrigeration process powering the Boomerang Nebula's record-setting cold, which we'll get to shortly. Thomson went on to become one of the most prolific scientists of his era, publishing more than 650 papers over the course of his career and holding patents on roughly 70 different inventions, while also playing a hands-on role in the successful installation of the first transatlantic telegraph cable. And the basic idea he was working with, the notion of some ultimate, unreachable, absolute cold, wasn't entirely new even in 1848. Earlier thinkers, including the chemist Robert Boyle back in 1665, and later Laplace, Lavoisier, and Dalton, had all turned the concept over in one form or another, long before anyone had the tools to measure it with any real precision. It took Thomson to turn that loose idea into a rigorous, usable scale, one that would eventually carry his name into every physics classroom and every scientific paper concerned with the deepest cold the universe has to offer, right up through the numbers we've already been discussing throughout this video. Here on the surface of the Earth, when something gets cold, we usually have an intuitive, almost automatic understanding of why. Cold air blows past your skin and pulls heat away from your body through a process called convection. Touch a metal railing outdoors in winter, and heat drains rapidly out of your hand, directly into that cold metal through a process called conduction. Both of those processes, convection and conduction, depend entirely on having something physical available to work with. Actual air molecules that can blow past you and carry your body heat away with them, or actual solid material that your skin can directly touch and exchange energy with, molecule by molecule, through direct contact. And that's exactly where deep space stops playing by the same familiar rules, because deep space is, for almost all practical purposes that matter to a spacecraft or an astronaut, a vacuum. There's essentially nothing there, no air, no fluid of any kind, hardly any particles whatsoever, spread so thin across such staggering distances that they might as well not exist for the purposes of transferring heat in any of the ways we're used to experiencing on the ground. There are exactly 3 ways that heat can move from one place to another, anywhere in the universe: conduction, convection, and radiation. Conduction requires direct physical contact between particles, passing motion from one to the next, the way one billiard ball transfers its momentum into the next ball the instant they collide on a pool table. Convection requires an actual fluid, a gas or a liquid, physically moving from a hotter region toward a cooler one and carrying its heat along for the ride, the same way a fan pushes cooler air across your skin, or the way water circulates through a heating system to warm an entire house. Both of those processes require something to work with: real, physical matter, positioned close enough together to bump into other matter, again and again, transferring energy through contact. And in the near total emptiness of a vacuum, neither one of those processes has anything at all to grab onto. There's nothing there to conduct heat through, and there's no fluid there to convect heat with, which leaves exactly one remaining option, the only one of the 3 that doesn't require any medium whatsoever: radiation. Radiation is fundamentally different from the other 2 mechanisms because it doesn't depend on the presence of matter at all. It travels as electromagnetic waves, and electromagnetic waves are perfectly capable of crossing completely empty space without any material to carry them along. This is, after all, precisely how the sun's warmth manages to reach us across roughly 93 million miles of largely empty distance to heat the surface of the Earth every single day. No air is required for that particular journey. No fluid carries the warmth along the way. The radiation simply crosses the emptiness entirely on its own, unassisted, and delivers its energy directly to whatever object it eventually strikes, whether that object happens to be a leaf, a rooftop, a human shoulder on a summer afternoon, or the hull of a spacecraft passing silently through the dark. So in deep space, radiation is the only game in town, both for gaining heat from any nearby source and for losing heat back out into the surrounding emptiness. And radiation, compared to conduction and convection, happens to be a relatively slow and inefficient way to move heat around. Which means, In a strange and almost counterintuitive way, objects in deep space are somewhat insulated from extremely rapid heat loss, even while sitting in an environment that we casually, and not entirely accurately, describe as simply freezing cold. This is part of why the popular, dramatic image of an object in deep space instantly freezing solid the moment it's exposed to the vacuum is more complicated and honestly more interesting than it first sounds. There's no medium out there capable of stripping heat away quickly, the way plunging your hand into ice water would strip heat from your skin within seconds. Instead, an object exposed to deep space radiates its heat away gradually, according to its own material properties and its own starting temperature, slowly drifting towards some eventual equilibrium point, a balance determined entirely by how much radiant energy it happens to be absorbing from any nearby star, weighed against how much energy it's simultaneously emitting back out into the emptiness surrounding it. Far from any star, with essentially nothing nearby to warm it, that equilibrium point ends up settling extremely, extremely low. And that brings us directly to the single number that effectively defines the baseline temperature of the entire universe, 2.7 Kelvin. There's also a fascinating wrinkle buried inside all of this, one that trips up even people who think they understand how spacecraft handle heat. In the upper reaches of Earth's atmosphere, in a layer called the thermosphere, the exact region where the International Space Station happens to orbit, the surrounding gas can technically reach temperatures as high as 3,600 degrees Fahrenheit, a number that sounds like it belongs to the surface of a star rather than to the neighborhood of an orbiting laboratory. And yet spacecraft flying through that region don't burst into flame, and astronauts inside them don't experience anything close to that kind of heat. The reason comes right back to the same core principle we just walked through. The thermosphere is so thin, so sparsely populated with actual gas molecules, that there simply aren't enough particles present, close enough together, to transfer that theoretical heat into a solid object through conduction or convection. Temperature, in that thin, wispy layer, is a measure of how fast individual molecules are moving. But with so few molecules actually colliding with the spacecraft's hull, almost none of that motion ever gets transferred as usable, felt heat. It's a striking example of just how differently temperature behaves once you strip away the atmosphere that we, on the ground, take completely for granted. To understand where that 2.7 Kelvin figure actually comes from, and why it applies almost everywhere across the observable universe, we have to travel all the way back to the very beginning of everything, to the Big Bang itself, roughly 13.8 billion years ago. In the earliest moments after the Big Bang, the universe existed as an unimaginably hot, unimaginably dense soup of particles and radiation, so thick and so energetic that light itself couldn't travel freely through it at all, constantly scattering off free-floating charged particles before it could ever get very far in any direction, the way headlights scatter uselessly inside a thick, rolling fog. That situation changed dramatically roughly 380,000 years after the Big Bang, when the universe had finally expanded and cooled down enough for electrons and protons to combine together into neutral, electrically balanced atoms for the very first time. At that specific moment, something remarkable happened. Space itself suddenly became transparent, almost overnight in cosmic terms, and light was finally set free to travel outward in long, unobstructed straight lines across the cosmos, the fog lifting all at once, everywhere, throughout the entire universe simultaneously. That light, released at that precise moment in cosmic history, was extraordinarily hot when it first set out on its journey. The temperature of the universe at that time was somewhere around 3,000 Kelvin, comparable to the surface temperature of a relatively cool, reddish star, glowing with intense, visible heat. But here's the crucial part. The universe didn't stop expanding once that light was released into the newly transparent cosmos. It kept stretching outward and stretching and stretching continuously for the next 13.8 billion years, all the way up to the present moment. And as space itself expanded, it stretched out the wavelength of that ancient light right along with it, a phenomenon astronomers call redshifting, because stretching a light wave shifts its color toward the red end of the spectrum, and beyond, into wavelengths our eyes can't even perceive. Stretch a light wave out far enough, and its effective temperature drops correspondingly, because for this particular kind of radiation, wavelength and temperature are directly, mathematically linked to one another. Over the entire history of the universe, that original 3000 Kelvin light has been stretched by a factor of roughly 1,100 times its original wavelength, and its effective temperature has dropped along with it, all the way down to approximately 2.7 Kelvin, or right around -270 degrees Celsius, equivalent to about -455 degrees Fahrenheit. The most precise scientific measurements available push that figure even further into decimal territory, landing somewhere around 2.725 to 2.726 Kelvin, with one particularly careful and rigorous analysis, conducted by astronomer D.J. Fixon of the University of Maryland and NASA's Goddard Space Flight Center, pinning the number down to 2.72548 Kelvin, with an uncertainty of only about half of 1,000th of a degree in either direction. That's an extraordinary degree of precision for a measurement describing something that happened nearly 14 billion years ago. This ancient, dramatically redshifted light is what astronomers call the cosmic microwave background, universally abbreviated as the CMB, and it represents, in a very real and literal sense, the oldest light in the entire universe that human instruments are capable of directly observing. It fills every single corner of the observable universe almost perfectly evenly, arriving from every possible direction in the sky at almost exactly the same intensity and almost exactly the same temperature, varying only by tiny fractions of a single degree from one direction to another, fractions so vanishingly small that early instruments couldn't detect them at all, no matter how carefully scientists searched. It eventually took extraordinarily sensitive, purpose-built space telescopes to finally map out those subtle temperature ripples across the entire sky, ripples that trace directly back to slight density variations present in the infant universe, variations that, over billions of years, gradually grew and clumped together into the galaxies, stars, planets, and eventually, on at least one small world orbiting one ordinary star, the astronomers capable of measuring them in the first place. The discovery of the cosmic microwave background stands as one of the great accidental breakthroughs in the entire history of science, and it happened in 1965, in circumstances that had absolutely nothing to do with a university observatory or a dedicated cosmology research program. It happened at Bell Labs in New Jersey, where two radio astronomers, Arno Penzias and Robert Wilson, were using a large, extremely sensitive antenna originally designed to detect faint microwave signals for entirely different, more practical purposes. No matter what they tried, they kept picking up a persistent, unexplained background static that they simply could not eliminate, no matter how carefully they checked and rechecked every piece of their equipment. They tested every wire, every connection, every possible source of electrical interference they could think of. At one point during their investigation, they discovered, almost comically, that a pair of pigeons had taken up residence directly inside the antenna structure itself, and they carefully removed the birds and cleaned out the accumulated mess the pigeons had left behind, genuinely hoping that this had finally solved the mystery once and for all. It hadn't. The static remained, stubbornly present, stubbornly uniform, arriving from every direction in the sky, at every hour of the day and night, regardless of exactly where they pointed the antenna or what time of year it happened to be. What Penzias and Wilson had stumbled onto, without initially realizing the full significance of what they were looking at, was the actual physical afterglow of the Big Bang itself. Direct, measurable, physical evidence, radiating in steadily from every direction at once, that the universe really had begun in an unimaginably hot, unimaginably dense state, and had been cooling and expanding ever since that very first moment. Their accidental discovery became one of the single strongest pieces of supporting evidence for the entire Big Bang theory, transforming what had been a compelling but not fully proven cosmological model into something resting on solid, directly observed evidence. It eventually earned both Penzias and Wilson a Nobel Prize, awarded for a discovery that began, essentially, with two frustrated scientists trying to figure out why their antenna wouldn't stop humming with static, and ended with humanity gaining direct physical access to light that had been traveling toward us for nearly 14 billion years. Penzias and Wilson's accidental discovery was only the beginning of the story, not the end of it. Once scientists knew the cosmic microwave background was really there, waiting to be studied in detail, NASA and later the European Space Agency began sending a series of increasingly sensitive satellites specifically designed to map it. The first was COBE, the Cosmic Background Explorer, which launched on November 18, 1989, carrying 3 separate instruments built specifically for this kind of work. One to hunt for a faint cosmic infrared background, one to map the CMB's temperature with high sensitivity, and one to measure its overall spectrum with extreme precision. COBE confirmed that the background radiation matched the Big Bang's predicted spectrum with remarkable precision, and in 1992 it detected, for the very first time, faint temperature ripples across the sky, differences of only about 1 part in 100,000, mapped at a resolution of roughly 7 degrees. That discovery was significant enough that 2 of COBE's lead scientists, John Mather and George Smoot, later shared the Nobel Prize in Physics in 2006. NASA's next mission, WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001 and pushed the resolution of these temperature maps down to better than half a degree, finding differences as small as reading 2.7251 Kelvin in one part of the sky and 2.7249 Kelvin in another, a level of precision almost impossible to picture. OneMap's data provided strong supporting evidence for cosmic inflation, the theory that the universe underwent a period of extraordinarily rapid expansion in its very earliest moments. Then came Planck, a European Space Agency mission launched in 2009 with significant NASA involvement, which sharpened the picture even further, resolving details as small as 1/12 of a degree across the sky, and refining the estimated age of the universe to 13.82 billion years. Each of these 3 missions, COBE, then WMAP, then Planck, effectively produced a progressively sharper baby picture of the infant universe, the same 2.7 Kelvin afterglow first stumbled upon by 2 frustrated radio astronomers cleaning pigeons out of an antenna, gradually coming into ever finer focus across 4 decades of dedicated space missions. So, in a very real sense, 2.7 Kelvin is the temperature of the universe's own leftover heat, the faint residual warmth of an explosion that happened nearly 14 billion years ago and has been fading, quietly and continuously, ever since, spread out so thinly across all of existence that it barely qualifies as warmth at all, anymore by any everyday human standard. This is the baseline. This is roughly what an object would eventually cool down to if you took it far, far away from any star, moon, or planet, and simply allowed it to sit undisturbed in the emptiness of deep space long enough to settle fully into equilibrium with its surroundings. Not absolute zero, not quite, but close enough that -270 degrees Celsius might as well be unimaginable to anyone standing on the surface of the Earth, where even the coldest recorded natural temperatures on our own planet don't come anywhere remotely close to that number. There are roughly 400 photons of this ancient cosmic microwave background light, packed into every single cubic centimeter of space throughout the observable universe, an almost inconceivably vast number of individual particles of light, and yet, spread this thin across all of existence, they carry so little collective energy that the temperature they produce sits barely above the absolute floor that physics allows. Before we get to the strangest natural cold spot of all, it's worth mentioning one more object, sitting just beyond the edge of our own solar system, that shows how far this baseline cold extends outward, even among the closest neighbors we have. It's called WISE 0855, and it's what astronomers classify as a brown dwarf, essentially a failed star, an object that formed the same way ordinary stars do, but never gathered enough mass to ignite nuclear fusion at its core. It was discovered in 2014 by Kevin Luhman, an astronomy professor at Penn State University, and it sits remarkably close to us in cosmic terms, somewhere around 7 light-years away, making it one of the closest known systems to our own Sun. Its estimated temperature comes in at around 250 Kelvin, roughly -23 degrees Celsius, genuinely cold by human standards, but nowhere near as extreme as the numbers we've already covered, since it's less than 5% of the Sun's surface temperature of nearly 5,800 Kelvin. What makes WISE 0855 scientifically interesting isn't just its temperature on its own, though. It's cold enough that researchers using the Spitzer Space Telescope and, more recently, the James Webb Space Telescope's instruments have detected apparent patchy clouds and shifting brightness in its atmosphere, along with carbon monoxide and signs of water, making it, in the words of Luhmann himself, especially well suited to observation by JUICE, since the coldest brown dwarfs are brightest at infrared wavelengths and extremely faint and difficult to observe at visible wavelengths. Estimates put its mass at somewhere between 3 and 10 times the mass of Jupiter, which makes it, in a very real sense, the closest thing astronomers have found to a genuine, directly observable analog of a giant planet sitting outside our own solar system. Cold enough that some researchers believe it may be the first object beyond Earth, Mars, Jupiter, and Saturn likely to host actual water clouds drifting through its visible atmosphere. Luhmann, incidentally, is also the astronomer who discovered the third closest system to our Sun, a separate binary brown dwarf pair called Luhmann 16, located about 6.5 light-years away, meaning one researcher personally identified 2 of the handful of closest neighbors our Sun has anywhere in the galaxy, both of them cold, dim, failed stars, rather than anything resembling our own bright Sun. And yet, and this is one of those details that seems almost purpose-built to break your intuition about how the universe is supposed to work, there is a place, a specific, real, physical location out there among the stars that is somehow colder than the background temperature of the entire universe itself. On the surface, that shouldn't be possible, based on the basic picture we just spent the last several minutes laying out. If 2.7 Kelvin really is the ambient temperature that everything in deep space eventually settles toward, given enough time and enough distance from any star, then nothing should ever be able to sit permanently below that line, because the cosmic microwave background itself, arriving steadily from every direction at once, should constantly be delivering just enough radiant energy to keep everything from dropping any further below it. And yet, there it is, sitting quietly in the constellation Centaurus, colder than the birth glow of the entire universe, the Boomerang Nebula. The Boomerang Nebula sits about 5,000 light-years away from Earth, and it was first spotted and formally named back in 1980, when astronomers Keith Taylor and Mike Scarrett observed it using a large ground-based telescope in Australia, and noticed its distinctive lopsided, curved shape in their images, which reminded them strongly of a boomerang, giving the object its now famous name. At the time of that initial observation, nobody had any real idea just how extreme this particular object actually was underneath its unusual visual appearance. That deeper discovery came 15 years later, in 1995, when astronomers Raghvendra Sahai and Lars-Åke Nyman pointed the 15-meter Swedish ESO sub-millimeter telescope, located high in the mountains of Chile, directly at the nebula and carefully, precisely measured its temperature for the very first time. What they found was genuinely staggering, roughly minus 272 degrees Celsius, just a single degree above absolute zero itself, and, remarkably, colder than the 2.7 Kelvin cosmic microwave background that fills the rest of the observable universe. It remains, as far as astronomers have been able to determine through decades of subsequent observation, the only known natural object anywhere in the universe that manages to sit consistently below that cosmic baseline temperature. So how, exactly, does an object out there in the vastness of space manage to get colder than space itself? The answer lies entirely in what the Boomerang Nebula actually is, physically, and in the specific, violent process currently unfolding at its center. It's what astronomers call a young planetary nebula, a term that, somewhat confusingly, has nothing at all to do with planets. It's simply the label astronomers historically gave to the glowing shell of expelled gas and dust, thrown off by a dying, sun-like star as it reaches the final, dramatic stages of its stellar life. At the very heart of the Boomerang Nebula, a central star is violently shedding its own outer layers, blasting gas outward at an extraordinary, almost incomprehensible speed of roughly 500,000 kilometers per hour, and it has been doing this continuously at an intense and sustained rate for approximately 1,500 years, losing something on the order of 1,000th of a solar mass of material every single year. a mass loss rate that astronomers estimate is somewhere between 10 and 100 times faster than what's typically observed in similar dying stars going through the same general process. That specific combination of factors, enormous outward velocity, sustained continuously over an unusually long period of time at an unusually high overall mass loss rate, turns out to be the key to the entire mystery, because rapidly expanding gas cools itself down through a very ordinary, very well understood physical process, one you've almost certainly experienced firsthand without ever thinking of it as a demonstration of astrophysics. It's the same basic principle at work inside a household refrigerator, and it's the same reason a can of aerosol spray feels distinctly cold to the touch immediately after you use it, because the compressed gas inside is expanding rapidly the instant it's released into the open air, and that rapid expansion pulls energy directly out of the surrounding material, cooling it in the process. Now scale that exact same principle upward, dramatically, to the level of an entire dying star, violently expelling its own outer atmosphere at hundreds of thousands of kilometers per hour, sustained continuously for well over a millennium, and you get a natural refrigeration process powerful enough to drag the surrounding gas down below the ambient background temperature of the entire universe itself, an achievement that no ordinary star, going through an ordinary, more gradual death, ever manages to replicate. For decades following its initial discovery, astronomers studied the Boomerang Nebula using whatever instruments happened to be available to them at the time, refining their understanding gradually, one observation at a time. In 2003, new images captured by the Hubble Space Telescope revealed what looked, at that point, like a fairly classic hourglass shape to the nebula, two roughly symmetrical lobes pinched together at the center, a structure familiar from many other dying stars observed throughout the galaxy. But the real breakthrough in understanding the nebula's true underlying structure came a full decade later, in October of 2013, when astronomers turned the Atacama Large Millimeter-Submillimeter Array, universally known by its acronym ALMA, based high in the mountains of Chile, toward the Boomerang Nebula for an entirely fresh, far more detailed and technically sophisticated look than anything possible before. What ALMA ultimately revealed was a structure that looked considerably less like a tidy, symmetrical hourglass and considerably more like a genuinely ghostly, wispy bow-tie shape, an eerie, almost delicate form, quite different from what the earlier Hubble images had originally suggested, forcing astronomers to reconsider exactly how the nebula's material was actually distributed in three-dimensional space. That 2013 study confirmed, once again, with even greater confidence than before, that the Boomerang Nebula holds the record as the coldest known object anywhere in the universe, colder even than the faint background radiation left over from the birth of the cosmos itself. A later scientific paper, published in 2017 by Sahai and his collaborators, dug even deeper into the underlying physics of the nebula's extraordinary ultra-cold outflow, tracing the cold gas outward to a genuinely staggering distance of roughly 120,000 astronomical units from the central star. To put that number into some kind of usable perspective, remember that one single astronomical unit is simply the average distance between the Earth and the Sun. So this ultra-cold outflow of gas stretches across a region of space more than 100,000 times wider than our entire Earth-to-Sun distance. A genuinely vast structure built entirely out of gas that has been cooled below the temperature of the universe itself. The researchers involved in that study estimated that this ultra-cold outflow contains at least 3 1/3 times the total mass of our own Sun, all of it expelled outward from a central star whose original mass, before it ever began this dramatic, violent process of shedding its outer layers, is estimated to have been at least 4 times the mass of the Sun. That same research also found evidence of a difference in age between the nebula's dense central waste and its faster-moving outflow, a kind of cosmic jet lag the researchers took as a sign that the dying central star likely isn't acting alone, but interacting directly with a companion star locked in orbit alongside it, shaping the whole structure together. There's an interesting wrinkle in the ongoing scientific study of the Boomerang Nebula that's worth mentioning here, because a good, honest documentary doesn't pretend that every single answer in science is permanently, finally settled the moment it's first announced. Some later observations have suggested that certain parts of the nebula appear to be gradually warming as the object continues to age over time, a development that could, at some point in the future, potentially cost the Boomerang Nebula its title as the single coldest known place in the universe. Nothing about that possibility is confirmed or fully finalized based on the available research, but it's a useful reminder that even the coldest known place we've ever managed to find isn't necessarily frozen in that exact position, forever, for all time. The universe keeps moving, keeps evolving, keeps changing, even out at the absolute extremes of what we can measure. It's also worth being precise about a small but genuinely important distinction here, one that sets up exactly where this story is ultimately heading. The Boomerang Nebula is accurately described as the coldest known object in the universe, but more specifically, it holds that title as the coldest object found in nature, meaning it's the coldest thing anyone has ever managed to find simply by pointing a telescope outward and searching the sky, rather than the single coldest temperature ever achieved anywhere by any means under any circumstances. And that particular distinction turns out to matter a tremendous amount, because as we're about to see later in this video, human beings, working carefully inside laboratories right here on planet Earth, have actually managed to go dramatically, almost unbelievably colder than the Boomerang Nebula, using nothing more exotic than magnets, lasers, and a great deal of patient, careful, methodical work. But before we get to that particular twist, let's bring the discussion back down to something a little more familiar and a little more human in scale: spacecraft, and the very real, very practical, very consequential challenge of surviving deep space's temperature extremes when you happen to be an actual piece of engineered hardware, built by human hands, rather than a slowly expanding cloud of gas that's been quietly cooling for the last 15 centuries. Before we leave the subject of naturally occurring cold behind and turn to human-built spacecraft, it's worth taking a quick tour of just how cold things get elsewhere across our own solar system, because the record for coldest measured spot doesn't actually belong to some far-off nebula or a distant planet. It belongs to a place almost embarrassingly close to home, our own moon. NASA's Lunar Reconnaissance Orbiter, launched in June of 2009, carries an instrument called the Diviner Lunar Radiometer Experiment, built to conduct the very first global temperature survey of the lunar surface. What Diviner found almost immediately was that certain craters near the moon's south pole contain regions that are permanently shadowed, areas that never once received direct sunlight, possibly for billions of years running, tucked away inside deeper craters nested within larger ones. Inside those permanently dark pockets, Diviner recorded temperatures as low as roughly -415 to -420 degrees Fahrenheit, somewhere around -248 to -250 degrees Celsius, or about 24 to 26 Kelvin. One specific measurement, taken in the floor of a crater called Hermite, came in at -415 degrees Fahrenheit, -248 Celsius, described by NASA at the time as the coldest temperature ever measured anywhere in the solar system. David Page, Diviner's principal investigator and a planetary scientist at UCLA, put it about as plainly as it can be put. Right here, in our own backyard, are definitely the coldest things we've seen in real measurements. He described the only source of warmth reaching those crater floors as little more than a faint glow. Ashwin Vasavada, a member of the Diviner science team at NASA's Jet Propulsion Laboratory, added that after decades of speculation, this was the first real confirmation that these strange, permanently dark, and extremely cold places actually exist on our moon at all. What makes that finding genuinely surprising is the comparison it invites. Those lunar craters turn out to be colder than the average surface temperature of Pluto, even though Pluto orbits roughly 40 times farther from the Sun than our own moon does. The difference comes down to the nature of the shadow itself. Pluto's cold is spread out across its entire surface, moderated by whatever faint, indirect sunlight manages to reach it from so far away. The lunar craters, by contrast, sit in total, permanent shadow, receiving no direct sunlight whatsoever, which lets them drop even further than a planet 40 times more distant from the Sun. A more recent characterization from the Diviner team describes some of these isolated shadowed regions, dropping as low as -420 degrees Fahrenheit, -250 degrees Celsius, colder, they note, than the surface of Pluto, and nearly 150 degrees Fahrenheit, colder than the coldest natural temperature ever recorded on Earth's own East Antarctic plateau. And that lunar cold sits right alongside some of the most extreme daily temperature swings anywhere in the solar system, because the very same moon that hides these permanently frozen craters also has an ordinary sunlit surface that averages around 107 degrees Celsius during the day and plunges to around -153 degrees Celsius at night. The specific craters involved have names now, places like Hermite, Faustini, Shoemaker, and Haworth near the lunar South Pole, and Peary and Bosch near the north. And researchers found that the coldest readings tended to come from craters tucked inside other, larger craters, hiding even deeper from any stray light that might otherwise sneak in at an angle. Some of the coldest, most remote pockets identified by the mission were so obscure they didn't even have names yet at the time of discovery. The Diviner team themselves put the scale of the finding plainly on their own mission website, noting that to find another object with a surface this cold, you would essentially have to travel out past the Kuiper belt itself. Except, as it turns out, you don't have to travel anywhere at all. It's sitting in our own backyard, a few permanently shadowed craters away. Speaking of Pluto, the numbers there are worth sitting with in their own right. Various NASA-affiliated sources place Pluto's surface temperature at somewhere around 40 Kelvin, roughly -233 degrees Celsius, or about -387 degrees Fahrenheit, with more detailed figures suggesting a mean surface temperature around 44 Kelvin, ranging from a maximum of about 55 Kelvin down to a minimum of about 33 Kelvin, depending on location and where Pluto happens to sit along its long, elliptical, 248-year orbit around the Sun. At that kind of temperature, nearly everything familiar to us on Earth, water, air, even ordinary gases we breathe without a second thought, would freeze completely solid on contact with the surface. Much of Pluto's icy landscape is made not of frozen water at all, but of frozen nitrogen, the same gas that makes up most of the air around you right now, condensed into large, transparent crystals several inches across. When New Horizons actually arrived at Pluto in 2015 and measured its atmosphere directly, scientists were caught off guard by just how cold it turned out to be. About 70 Kelvin, -203 degrees Celsius, noticeably colder than the roughly 100 Kelvin researchers had predicted beforehand. Researcher Zhi Zhang described it as an ongoing mystery, noting that Pluto appears to be the first known planetary body where the atmosphere's overall energy balance is dominated by solid haze particles rather than by gases, the way it is on most other worlds. Then there's Uranus, which holds the outright record for the coldest atmospheric temperature ever, directly measured on any planet in the solar system, 49 Kelvin, about -224 degrees Celsius, detected by Voyager 2 back in January of 1986, in a specific cold spot located in the planet's tropopause, roughly 30 degrees south of its equator. Scientists still don't fully understand exactly what mechanism produces that particular cold pocket. What makes Uranus especially strange is that, despite sitting closer to the Sun than Neptune, it's generally considered the coldest planet overall, because Neptune continues to radiate a meaningful amount of leftover internal heat from its formation, while Uranus, for reasons still not entirely understood, radiates almost none of its own internal heat at all. Uranus is also famous for its bizarre axial tilt, rolling around the Sun on its side at more than 97 degrees, which means each of its poles spends a quarter of every 84-year Uranian year pointed almost directly at the Sun, while the rest of the planet sits locked in a long, dark winter. And that strange geometry only adds to the mystery of exactly why its internal heat behaves the way it does. And out at Neptune, its large moon Triton adds one more entry to this tour. Surface temperature estimates from the Voyager era place Triton somewhere around 34 to 38 Kelvin, roughly -235 to -238 degrees Celsius, cold enough that nitrogen gas in its thin atmosphere actually freezes solid and falls onto the moon's surface as frost. It's worth grounding all of this against something familiar before we move on. The coldest natural temperature ever recorded anywhere at ground level on Earth was -89.2 degrees Celsius, -128.6 degrees Fahrenheit, measured at the Soviet Vostok station in Antarctica on July 21, 1983, a number that already sounds almost unsurvivable by ordinary human standards, and yet it's still roughly 160 degrees Celsius warmer than the coldest shadowed pockets found on our own moon, just a few 100,000 miles away. With that tour of the solar system's coldest natural corners behind us, let's turn from places that are simply cold because nature happened to put them far from the sun, or tucked permanently into shadow, to places that are cold because human engineers designed them that way, on purpose, under enormous pressure, with human lives sometimes depending directly on getting the numbers right. Consider the International Space Station, orbiting a few hundred kilometers above the surface of the Earth, circling the entire planet roughly once every 90 minutes. Because of that remarkably fast orbital speed, the station experiences 16 separate sunrises and 16 separate sunsets every single day, constantly, repeatedly passing between direct, completely unfiltered sunlight and the total, absolute darkness of Earth's shadow, over and over, in a rhythm that has nothing to do with the 24-hour day that governs life on the surface below. Without any kind of thermal control system in place to actively manage the situation, the sun-facing side of the station would heat up to roughly 250 degrees Fahrenheit, that's about 121 degrees Celsius, hot enough to be genuinely dangerous to touch, while at the very same instant in time, the shadowed side of that exact same connected structure would plunge to around -250 degrees Fahrenheit, or about -157 degrees Celsius. That works out to a swing of roughly 500 degrees Fahrenheit, or about 277 degrees Celsius, occurring across a single, continuous, physically connected structure at the very same moment, with essentially no gradual blending or transition between the two extremes, because there's no atmosphere out there in orbit to mix those temperatures together the way weather systems mix hot and cold air masses together here on the surface of Earth. And yet, inside the station, astronauts live and work in a perfectly comfortable, thoroughly ordinary environment, kept at somewhere around 22 to 24 degrees Celsius, or 72 to 75 degrees Fahrenheit. Essentially, standard room temperature, the same comfortable range you'd expect to walk into inside any well-managed office building here on Earth. That comfort, sitting just meters away from temperature swings of nearly 500 degrees Fahrenheit, is entirely the product of the station's dedicated thermal control system, an intricate network of engineering solutions built specifically to counteract the brutal, relentless swings happening constantly just outside the hull. One of the cleverest pieces of that overall system is the specific choice of coolant fluid. Rather than using ordinary water, which would freeze completely solid at the coldest external temperatures the station regularly experiences, engineers instead use liquid ammonia, a substance that remains in liquid form at a much lower temperature, staying liquid down to around -108 degrees Fahrenheit, or about -77.7 degrees Celsius. That liquid ammonia continuously circulates through the station's internal systems, quietly absorbing excess heat generated by electronics, life support equipment, computer systems, and the astronauts' own bodies as they move, work, and exercise throughout their day, then carrying all of that accumulated heat outward to external radiator panels, where it's finally released back out into space in the only way heat is ever able to leave a spacecraft while sitting inside a vacuum, through radiation. Remember, out in the vacuum immediately outside the station's hull, there's no air and no fluid available for the station to simply dump excess heat into directly, the way a car radiator dumps heat into the passing air, or the way your own body dumps heat into a cool breeze. Radiation is the only available option, and as we already established earlier, it's a comparatively slow, comparatively inefficient process for moving heat from one place to another. That inherent inefficiency is part of why the temperature swings just outside the station's hull can get so extreme in the first place. There's simply no fast, convenient way to even those temperatures out the way convection naturally does here on the ground. When engineers actually sat down and calculated the true average external temperature experienced by something orbiting at the station's altitude, once you carefully account for how much time it spends in full, direct sunlight versus partial shadow versus complete, total darkness over the course of a full orbit, the resulting figure lands at around 50 degrees Fahrenheit, noticeably warmer than the simple mathematical midpoint you'd get by just averaging the two extremes together, because the station actually spends more of each orbit exposed to at least some degree of sunlight than it spends sitting in complete, unbroken shadow. Astronauts don't just experience these dramatic extremes passively from the safety and comfort of a climate-controlled station interior either. When they step outside for a spacewalk, wearing what NASA officially calls the Extravehicular Mobility Unit, or EMU for short, they are stepping directly into an environment that can swing between roughly 121 degrees Celsius in direct sunlight and roughly minus 157 degrees Celsius in shadow, and their suit has to function as an entire personal, self-contained spacecraft in order to keep them alive and functional through both of those brutal extremes, often within the span of a single spacewalk lasting several hours. Underneath the suit's outer layers, astronauts wear a specialized garment lined with long, thin tubes filled with continuously circulating water, pushed along by a small but genuinely powerful pump built directly into the suit's life support systems. As the astronaut works through the intense, sustained physical exertion that a spacewalk demands, turning bolts, carrying equipment, maneuvering their own body weight against nothing but the suit's own inertia, that circulating water absorbs heat directly from their body through the tubing and carries it away, functioning almost like a portable, wearable, miniaturized version of the station's own larger ammonia cooling loop. On the outside of the suit, the outermost layer is bright white, a color chosen quite deliberately and specifically to reflect away as much incoming solar heat as possible before it ever has a chance to penetrate further inward. Layered together with genuinely tough Kevlar material, woven in to guard against the ever-present danger of micrometeorite impacts, alongside additional thermal insulation layers specifically designed to keep whatever heat does get through distributed evenly around the astronaut's entire body, rather than allowed to concentrate dangerously in any single spot. There's something worth sitting with for a moment here, something almost poetic, buried inside a piece of highly technical engineering. A spacesuit is, in the most literal and immediate sense imaginable, a miniature, wearable version of everything we've been discussing throughout this entire video so far. It has to manage the total absence of any atmospheric buffer whatsoever. It has to deal with radiation as effectively the only available mechanism for shedding excess heat, exactly the same fundamental constraint facing the entire space station and every spacecraft ever built. And it has to somehow keep a single, fragile human body safe, functional, and reasonably comfortable, while suspended directly between temperatures hot enough to be genuinely dangerous and temperatures cold enough to be equally dangerous, sometimes separated by only a few feet of physical distance, with nothing but the presence or absence of direct sunlight determining which extreme a given part of the suit happens to be facing at any given moment. Now let's push much further outward, past low Earth orbit entirely, out into the true, distant depths of the solar system, where sunlight eventually becomes so faint and so weak that it can no longer be relied upon to power a spacecraft at all, no matter how large its solar panels might be built. This is the environment that Voyager 1 and Voyager 2 have been quietly, steadily operating within for decades now, far longer than anyone involved in their original design ever seriously expected. Voyager 2 actually launched first, lifting off on August 20th, 1977, followed shortly afterward by Voyager 1 on September 5th of that same year, launched second but placed on a faster trajectory that ultimately carried it past its twin. Both spacecraft were designed as part of what became known as a grand tour of the outer planets, taking advantage of a rare planetary alignment to visit multiple worlds using a single mission, and both have long since surpassed every original expectation ever placed on them by the engineers who built them. Voyager 1 crossed into interstellar space on August 25, 2012, becoming the very first human-made object in history to leave the heliosphere entirely, the vast, invisible bubble of charged particles blown continuously outward by our own sun that surrounds the entire solar system. Voyager 2 later followed its twin into that same interstellar environment. As of a report from the 2010s, Voyager 1 sits more than 11 billion miles away from Earth, making it, without any real competition, the single most distant human-made object currently in existence anywhere, continuing to drift steadily further away with every single passing year, sending back data across a gap that light itself takes many hours to cross. Out at that kind of staggering distance, sunlight becomes far too weak and far too diffuse to power anything genuinely useful through ordinary solar panels, which is precisely why both Voyager spacecraft rely instead on something called a radioisotope thermoelectric generator, universally abbreviated as an RTG. Rather than converting incoming sunlight into usable electricity the way solar panels do, an RTG generates its power directly from heat, specifically the steady, predictable heat continuously released by the natural, ongoing radioactive decay of plutonium-238. Each Voyager spacecraft carries 3 of these generators, using a specific design known as the multi-100-watt RTG, and together, these 3 generators don't just power the spacecraft's various instruments, onboard computers, and radio communication equipment. They also directly warm the spacecraft's own physical structure, which turns out to be absolutely critical to the mission's survival, because without that continuous internal warmth, the extreme cold of deep space would very quickly render Voyager's delicate electronics and precise mechanical systems completely inoperable, freezing them solid and permanently ending the mission. On top of the 3 main RTGs, each spacecraft also carries 9 additional, smaller radioisotope heater units, whose entire dedicated job is simply to generate a small, steady, reliable trickle of warmth, specifically aimed at keeping the most sensitive instruments from freezing. Here's the central, quietly dramatic challenge, though, and it's one that has patiently defined the entire second half of the Voyager mission, unfolding gradually over decades rather than happening all at once. Plutonium-238 decays at a completely predictable but entirely unstoppable rate, which means the heat it produces, and therefore the electricity the RTGs are able to generate from that heat, gradually, steadily declines year after year, decade after decade, with absolutely no way to refuel the generators or replace their aging fuel from a distance of billions of miles. Each individual MHW RTG initially generated about 158 watts of power at the moment of launch back in 1977, and by the time 2019 rolled around, roughly 42 years into the overall mission, Voyager's total combined power output had already fallen by about 40% compared to those original launch day figures, declining at a steady, measurable rate of roughly 4 watts of electrical power lost per year, year after year, without exception. By November of 2023, NASA reported that the spacecraft's power output had stabilized at around 225 watts total, only a fraction of what it once produced at launch, carefully managed and closely monitored by a dedicated mission team that has had to make increasingly difficult, increasingly consequential decisions about exactly which heaters and which scientific instruments can still be justified and kept running, and which ones, painfully, have to be permanently sacrificed to the encroaching cold, simply in order to keep the rest of the spacecraft alive and communicating with Earth for a few more years. That's a genuinely strange, slow-burning kind of drama, when you really stop to think carefully about it. Voyager isn't threatened by any single, sudden, dramatic event out there in the emptiness of interstellar space. There's no meteor storm bearing down on it, no catastrophic single-point mechanical failure waiting to strike without warning. Instead, it's a slow, quiet, decades-long negotiation, playing out continuously between a shrinking, ever-dwindling supply of internal heat and the relentless, patient cold pressing in steadily from every direction at once, instrument by instrument, watt by watt, year by year, as engineers back on Earth try to carefully squeeze every last useful year of scientific data out of 2 spacecraft that have already outlived their original mission plans several times over, using nothing more than careful budgeting of an ever-shrinking amount of warmth. Voyager isn't alone out there in relying on this particular kind of nuclear-powered warmth to survive the depths of space. New Horizons, which launched on January 19, 2006, made its historic, long-awaited flyby of Pluto on July 14, 2015, using a single RTG carrying about 24 pounds, or roughly 11 kilograms, of plutonium oxide fuel to keep its scientific instruments powered, functioning, and, just as importantly, warm, at a distance from the Sun where sunlight had become almost entirely negligible as a usable energy source. After its historic encounter with Pluto, New Horizons kept right on going, continuing to push deeper and deeper into the Kuiper Belt, the vast, distant region of icy, ancient bodies orbiting far beyond Neptune's own orbit, a region where sunlight is described by researchers as being reduced to little more than a faint, barely perceptible glow on the horizon. On January 1, 2019, New Horizons flew directly past a small, ancient Kuiper Belt object known as Arrokoth, at a distance of more than 4 billion miles away from Earth. At the time, this represented the single farthest planetary flyby ever conducted in the entire history of human space exploration, a record that stood as a genuine milestone for how far a functioning spacecraft could travel and still successfully complete a scientific mission. RTGs of this same general type have also quietly powered a long list of other historic missions over the decades, including scientific experiments deliberately left behind on the lunar surface during the Apollo missions. The International Ulysses mission, which used its own RTG to survey the Sun and Solar System for more than 18 years on a long, looping orbit that carried it all the way from Jupiter to the Sun's own poles. The Cassini spacecraft, which spent over a decade orbiting Saturn after launching in October of 1997 using 3 separate RTGs, and even present-day robotic explorers like the Curiosity and Perseverance rovers currently operating on the surface of Mars, which rely on this exact same basic nuclear principle to keep functioning safely and reliably through the bitterly cold Martian nights. The underlying physics inside these generators is almost poetic in its own strange and understated way, once you really picture what's happening inside the metal casing. Near the plutonium core, at the very center of an RTG, temperatures can reach around 1000 degrees Fahrenheit, or about 538 degrees Celsius, an almost furnace-like level of heat, generated entirely and continuously by the slow, steady, natural decay of radioactive material, requiring no moving parts, no combustion, no external fuel supply of any kind. Meanwhile, on the exact opposite side of that same compact generator, external radiator fins are exposed directly to the surrounding cold of deep space, dropping down to several hundred degrees below zero on that outward-facing side. Inside each of Voyager's own generators specifically, more than 300 individual silicon-germanium thermoelectric couples sit wired between a hot junction, originally around 1273 Kelvin, roughly 1000 degrees Celsius, and a cold junction sitting around 573 Kelvin, about 300 degrees Celsius, and it's precisely that internal temperature difference engineered directly into the hardware that the generator converts into usable current. That enormous sustained temperature gradient, blistering heat radiating from one side, profound cold pressing in from the other, is exactly what the generator is deliberately engineered to exploit, converting that difference directly into a steady, reliable, continuous trickle of usable electricity that has kept humanity's most distant machines alive, functioning, and faithfully communicating with Earth, decade after decade, far longer than anyone who originally designed and built them ever seriously expected to see. There's another mission worth mentioning here, because it represents the only time humanity has ever actually landed a spacecraft anywhere in the outer solar system, and it happened in conditions defined entirely by extreme cold. The Cassini-Huygens mission, a joint project between NASA, the European Space Agency, and the Italian Space Agency, launched on October 15, 1997, carrying NASA's Cassini orbiter and ESA's small, wok-shaped Huygens lander bolted to its side. For almost the entire 7-year journey out to Saturn, Huygens sat dormant in a kind of sleep mode, waking only briefly every 6 months for a few hours at a time, so engineers could confirm its systems were still functioning. On January 14, 2005, Huygens finally separated and descended by parachute through the thick, hazy atmosphere of Saturn's largest moon, Titan, a descent that took 2 hours and 27 minutes before touching down on the surface. Titan itself sits at a surface temperature of about -180 degrees Celsius, -292 degrees Fahrenheit, and remarkably, it's the only moon anywhere in the solar system with a genuinely dense atmosphere, thick enough that the surface pressure is about 60% greater than Earth's own. During its fiery descent through that thick atmosphere, Huygens' heat shield endured intense frictional heating, reaching temperatures reported anywhere from roughly 1,500 to as high as 18,000 degrees Celsius, depending on the specific measurement cited, an almost absurd extreme of heat generated entirely by slamming into a moon whose actual surface waits at nearly 180 degrees below zero. Once safely down, Huygens kept transmitting data back through Cassini for roughly 70 minutes or more, longer than engineers had originally expected, thanks partly to the probe's thermal insulation, which kept its own interior hovering around a comfortable 25 degrees Celsius, according to Huygens' mission manager Jean-Pierre Le Breton, even while the moon's surface outside sat locked at nearly -180. To this day, more than 2 decades later, that single landing remains the only time any spacecraft from Earth has ever successfully touched down anywhere in the outer solar system. A brief, cold, 70-minute conversation with an alien moon, conducted from more than 1 billion kilometers away. Titan sits so far from the Sun, roughly 10 times Earth's own distance, that sunlight arriving there carries only about 1% of the strength it has back home, and Titan's thick haze cuts down on whatever usable light does arrive even further still, which is exactly why NASA's next planned mission to Titan, a rotorcraft lander called Dragonfly, is being built around the same basic RTG technology that kept Voyager alive, rather than depending on solar panels the way many inner solar system missions do. Titan itself is the second largest moon anywhere in the solar system, smaller only than Jupiter's Ganymede, and it's larger than both the planet Mercury and the dwarf planet Pluto, which makes it a genuinely substantial world in its own right, not some minor icy afterthought orbiting Saturn, and it's a world that, despite its size, sits permanently locked at a temperature colder than anywhere human beings have ever lived, colder even, by a wide margin, than the coldest inhabited research stations scattered across Antarctica. There's one more spacecraft whose relationship with the cold of deep space deserves its own fully dedicated section, and it represents a very different kind of story from Voyager or New Horizons, because this particular spacecraft doesn't merely have to survive the cold as an unwelcome hazard to be endured. It actually needs the cold deliberately, precisely, in extraordinarily fine-tuned amounts in order to accomplish its scientific mission at all. That spacecraft is the James Webb Space Telescope. But to understand why Webb was built the way it was, it helps to look briefly at the mission that came before it and quietly worked out many of the same lessons the hard way. That earlier mission was the Spitzer Space Telescope, originally launched under the more technical name SIRTF, the Space Infrared Telescope Facility, before being renamed a few months into its mission, once engineers confirmed everything was working as intended. It was the fourth and final entry in NASA's series of great observatories, launched on August 25, 2003, and finally decommissioned on January 30, 2020, after more than 16 years spent scanning the sky in infrared light. Spitzer needed to be cold for exactly the same underlying reason Webb would later need to be cold, to keep the telescope's own warmth from drowning out the faint infrared signals it was trying to detect. Engineers cooled Spitzer using a substantial onboard supply of liquid helium, on the order of a few hundred liters depending on exactly which figure you look at, chilling the telescope down to around 5 Kelvin, about -450 degrees Fahrenheit, or -268 degrees Celsius, specifically to keep the observatory's own body heat, so to speak, from interfering with its observations of much colder cosmic objects. More precisely, Spitzer's overall telescope structure stayed below 8 Kelvin, while its detector focal planes, handling the longest wavelengths, were held colder still, down around 1.4 Kelvin. What made Spitzer especially clever for its era was an innovation in how it achieved that cold in the first place. Rather than launching already pre-chilled, Spitzer launched warm and cooled gradually in orbit, combining passive radiative cooling helped enormously by a distant, Earth-trailing solar orbit that kept it away from our planet's own residual heat, with the slow, careful boil-off of its onboard liquid helium supply. That combination reduced the mission's launch mass and stretched its useful cryogenic lifetime well beyond what a helium supply alone could have managed. The mission was originally designed to last only about 2.5 years in its fully cryogenic state. Through careful, economical use of the coolant, engineers stretched that all the way to about 5.5 years before the helium finally ran out around May 15, 2009. Sean Carey, manager of the Spitzer Science Center, summed up the team's reaction plainly. If the mission had only lasted 2.5 years, they would have met their original goals, but instead, in his words, "We were ecstatic with 5." Even after the helium was gone, Spitzer kept working for another decade in what NASA called its warm mission phase, relying purely on passive cooling to hold its 2 shortest wavelength imaging channels at a still frigid 26 to 29 Kelvin, continuing to gather data all the way to its eventual retirement in 2020. Along the way, Spitzer became the first telescope ever to directly detect light from a planet outside our solar system, discovered an enormous, previously unknown ring around Saturn in 2009, and helped identify TRAPPIST-1, the first known star system containing 7 roughly Earth-sized planets, a discovery that reshaped how astronomers think about the sheer variety of planetary systems scattered across the galaxy. All of it made possible because engineers found a clever, patient way to keep one small telescope cold enough, for long enough, far out past the warmth of our own planet. To appreciate how clever that innovation really was, it helps to look at what came before it. Earlier infrared missions had relied entirely on brute force helium supplies, without Spitzer's passive cooling trick, and they paid for it in mission length. IRAS, the first dedicated infrared astronomical satellite, carried roughly 500 liters of liquid helium on board, but managed only about 10 months of operation before running dry. Europe's ISO mission carried more than 2,300 liters, over 6 times as much, and still only stretched to about 2.5 years. Spitzer, by comparison, managed 5.5 fully cryogenic years using a fraction of that helium supply, simply by combining its onboard coolant with the patient, unglamorous physics of letting a well-shielded telescope radiate its own heat away into the emptiness around it. Spitzer's basic strategy: shield a telescope from the sun, let it radiate its own heat away into the cold of surrounding space, and supplement that passive cooling with a dedicated cryogenic system when the science demands something colder still, is the direct conceptual ancestor of the much larger, far more elaborate cooling system NASA and its partners would go on to build for the James Webb Space Telescope nearly 2 decades later. Webb is an international mission led by NASA in close partnership with the European Space Agency and the Canadian Space Agency, and it was built specifically to observe the universe in infrared light, a part of the electromagnetic spectrum that allows astronomers to peer directly through thick clouds of cosmic dust and observe extraordinarily distant, extraordinarily ancient galaxies that formed not very long, in cosmic terms, after the Big Bang itself. But there's a fundamental, almost paradoxical problem built directly into that mission from the very start. Infrared light is, at its core, essentially heat radiation. And if the telescope's own structure happens to be warm, even slightly warm, its own components will constantly radiate infrared light of their own, drowning out the impossibly faint infrared signals arriving after traveling for billions of years across the universe. In order to actually see clearly, Webb doesn't just need to avoid the direct heat of the sun. It needs to become extraordinarily, almost impossibly cold itself, colder than nearly anything else humans have ever deliberately built and launched into space. The first, and by far the largest part of that overall cooling process, comes from Webb's sun shield, an enormous 5-layer structure, roughly the size of a full tennis court, carefully engineered to block not just direct incoming sunlight, but also reflected light, bouncing off the surfaces of both the Earth and the Moon. Everything positioned on the shielded, protected side of that sun shield is left to cool entirely passively, simply by continuously radiating its own residual heat outward into the surrounding emptiness of deep space, with the sun shield itself preventing any significant new heat from ever making its way back in from the sunward side. Through that passive process alone, without any active mechanical cooling involved at all, Webb's instruments cool down to around 90 Kelvin, roughly minus 183 degrees Celsius, or minus 298 degrees Fahrenheit. Already colder than almost anything most people will ever personally encounter in their entire lives. And remarkably, that's still only the very first stage of the telescope's overall cooling process. Webb's actual mirrors, the enormous gold-coated segments that gather and focus incoming starlight, settled at slightly different final temperatures, depending on their exact physical position relative to the sun shield and the rest of the spacecraft's supporting structure, with the primary mirror segments ultimately ranging anywhere from about 34.7 Kelvin up to about 54.5 Kelvin, and the telescope's secondary mirror eventually reaching a final resting temperature of around 29.2 Kelvin. Even the exact angle the sun shield happens to be facing matters here, something engineers call the telescope's pointing attitude. A small amount of residual heat always manages to sneak through the 5-layer sun shield to reach the primary mirror, and how much gets through depends on that attitude. Because the mirror segments themselves change temperature so slowly, their actual reading at any given moment really reflects an average of several days' worth of pointing, not just the current instant. During its early commissioning phase, Webb spent much of its time pointed toward the ecliptic poles, an orientation NASA's own mission team described at the time as a comparatively hot attitude, relative to other directions the telescope could be aimed. Webb's near-infrared instruments, including 2 specific instruments called NARCam and NIRIS, are actively maintained using small onboard heating elements at a steady 38.5 Kelvin, while a separate instrument called NARSPEC is deliberately kept slightly warmer than the others, held at around 42.8 Kelvin, according to the exact requirements of its own specific detectors. But one particular instrument on board needed to go dramatically colder than all the rest of the observatory combined: the mid-infrared instrument, universally known by its acronym MIRI, which observes even longer infrared wavelengths than any of Webb's other cameras and sensors. MIRI's detectors are constructed from a highly specialized material, a specific formulation of arsenic-doped silicon that simply cannot function correctly or produce usable scientific data unless it's continuously held below 7 Kelvin, a temperature so extreme that passive cooling alone, no matter how effective the sun shield happened to be, could never realistically get it there entirely on its own. To reach that level of cold, Webb carries a dedicated, electrically powered cryocooler, a purpose-built refrigeration system engineered specifically to chill MIRI down far below the rest of the observatory's already extremely cold operating temperature. Actually getting there wasn't simple, and it took months of careful, patient work by engineers monitoring the process from the ground. Along with Webb's 3 other main instruments, MIRI initially cooled passively in the deep shadow of the sun shield, dropping down to around 90 Kelvin right alongside everything else on board. From that starting point, the dedicated cryocooler system took over the process, gradually pulling MIRI's internal temperature down further and further, working through a series of increasingly difficult, increasingly delicate engineering stages. The single hardest step of the entire cooling process earned its own memorable nickname among the engineering team responsible for it: the pinch point, referring to the critical, high-stakes moment when the instrument had to drop from 15 Kelvin all the way down to 6.4 Kelvin in one carefully managed operation. Annalyn Schneider, the MIRI project manager at NASA's Jet Propulsion Laboratory, described the tension surrounding that particular moment quite candidly. The cooler team had poured an enormous amount of effort into developing the exact, precise procedure needed to safely get through the pinch point, and the team was, in her own words, both excited and nervous going into the critical activity. In the end, everything went off exactly according to plan. In her description, a textbook execution of the procedure, with the cooler actually performing even better than the team had originally expected going into that critical moment. On April 7, 2022, MIRI officially reached its final operating temperature, dropping below 7 Kelvin, equal to roughly minus 266 degrees Celsius, or minus 447 degrees Fahrenheit. Gillian Wright, the European principal investigator for MIRI and director of the UK Astronomy Technology Centre, reflected afterward on exactly what that particular milestone meant, following so many years of dedicated preparation leading up to it. She said she was delighted that, after so much hard work by the entire MIRI team, the instrument was finally cold and ready for the next steps in the mission, adding that the simple fact the cooler had worked so well was itself a major achievement for the mission as a whole. There's a genuinely elegant piece of engineering hidden inside that cryocooler design that's worth pausing on for a moment, because it represents a real, meaningful leap forward compared to earlier cryogenic space telescopes that came before Webb. In the past, missions requiring extremely low operating temperatures often relied on slowly boiling off a limited, finite supply of liquid helium and simply venting the resulting gas away permanently into space. An effective approach in the short term, but ultimately a finite, disposable resource that inevitably runs out entirely, placing a hard, unavoidable expiration date on the mission's most sensitive observations. MIRI's cryocooler, instead, reuses its helium continuously in a closed loop, conceptually quite similar to the way an ordinary household refrigerator continuously recycles the exact same coolant over and over again, indefinitely, rather than consuming and permanently discarding it with each use. That single, thoughtful design choice means MIRI isn't racing against a fixed countdown timer the way older missions inevitably were. As long as the cryocooler mechanism itself keeps functioning correctly, it can, in principle, keep MIRI at its extreme operating temperature indefinitely, for as long as the rest of the observatory remains operational. Getting there in the first place required cooling roughly 100 kilograms, about 220 pounds, of metal, glass, and electronics, all the way down from the temperature it carried on a warm, humid Florida launch morning, through every intermediate stage, to its final, frigid operating point. A gradual process that took approximately 3 months from start to finish, unfolding slowly and carefully across the emptiness of space on the journey out to its final observing position. So here we have a telescope floating roughly 1 million miles from Earth, deliberately, painstakingly engineered to be one of the coldest human-made objects ever sent into space. Not because that extreme cold is some unfortunate hazard to be grudgingly tolerated or worked around, but because the cold is, in a very real sense, the entire point of the design, the very thing that ultimately allows the telescope to see clearly enough to observe some of the earliest, most distant galaxies that have ever existed, light that has been traveling toward us since not long after the very beginning of everything. And now, finally, we arrive at the twist we mentioned much earlier in this video, the detail that quietly undercuts almost everything you might naturally assume about where the coldest place in the entire universe ought to logically be found. Because as extraordinary as the Boomerang Nebula genuinely is, sitting at roughly -272 degrees Celsius, and as extreme as MIRI's operating temperature genuinely is, sitting below 7 Kelvin, neither one of them comes anywhere close to the actual coldest temperatures ever recorded, anywhere, by anyone. Those records don't belong to deep space at all. They belong to laboratories, built entirely by human hands, sitting right here on the surface of planet Earth. To understand how human beings ever got into the business of manufacturing colder than space in the first place, it helps to go back more than a century, to a laboratory in the Netherlands and a physicist named Heike Kamerlingh-Onnes. Born in Groningen in 1853, Onnes spent decades at the University of Leiden developing better and better techniques for cooling gases down toward absolute zero, eventually founding a large, dedicated cryogenics laboratory there in 1904. On July 10, 1908, after years of painstaking work building on an already successful hydrogen liquefaction machine, Onnes achieved something no one had managed before. He successfully liquefied helium, the most stubborn gas of all to cool, using a chain of pre-cooling stages built around the same Joule-Thomson effect that Lord Kelvin himself had helped describe decades earlier. Liquid helium boils at around 4.2 Kelvin, roughly -269 degrees Celsius, and by carefully reducing the pressure on that liquid helium even further, Onnes managed to push the temperature down to around 1.5 Kelvin, the coldest temperature achieved anywhere on the planet at that point in history. The achievement earned his laboratory in Leiden an informal but well-deserved nickname, the coldest place on Earth. 3 years later, on April 8, 1911, while studying how a solid mercury wire behaved when submerged in his liquid helium, Onnes noticed something that seemed almost impossible. At 4.2 Kelvin, the wire's electrical resistance didn't just drop. It vanished completely, instantly, as if the mercury had stopped resisting the flow of electricity altogether. Onnes recognized immediately that he'd found something genuinely new, writing in his notes that mercury had passed into a new state, which, on account of its extraordinary electrical properties, could be called the superconductive state. He had discovered superconductivity, and that same afternoon, he also became the first person to observe a related phenomenon called superfluidity, noting that just before the coldest point of his experiment, the boiling of his helium bath suddenly stopped and the liquid began visibly shrinking instead. Onnes won the Nobel Prize in Physics in 1913 for his work liquefying helium, and it would take another 46 years before physicists John Bardeen, Leon Cooper, and J. Robert Schrieffer finally worked out the full theoretical explanation for why superconductivity happens at all. That discovery, made in a Dutch laboratory more than 100 years ago, using nothing more sophisticated than careful engineering and an obsessive dedication to reaching lower and lower temperatures, turns out to be the exact reason a certain enormous machine buried underground in Europe today has to be one of the coldest places on the entire planet. The first hint of that twist doesn't even require leaving Earth's surface or venturing into the world of ultra-specialized quantum physics labs. It's sitting underground, straddling the border between France and Switzerland, inside the Large Hadron Collider, the enormous particle accelerator operated by CERN. The LHC's main superconducting magnets are cooled to 1.9 Kelvin, about -271.3 degrees Celsius, a temperature that CERN itself describes as colder than the roughly 2.7 Kelvin average temperature of outer space. By CERN's own description, this makes the LHC one of the coldest places anywhere on the surface of the Earth. That extreme cold isn't an incidental side effect or an engineering flourish, it's an absolute requirement. The LHC relies on roughly 1,650 main magnets that need to operate in a superconducting state, meaning electrical current can flow through them with essentially zero resistance, in order to generate magnetic fields powerful enough to steer and tightly focus proton beams traveling at nearly the speed of light around the accelerator's 27-kilometer underground ring. Without reaching that specific temperature, the magnets simply would not work at all. Getting there happens in careful stages. During the first stage, as each roughly 3.3-kilometer sector of the ring cools down to about 80 Kelvin, just above the temperature of liquid nitrogen, the steel structures themselves physically shrink by about 3 millimeters for every meter of length, adding up to nearly 10 meters of contraction across a single sector, which engineers had to plan for in advance, using expansion bellows and deliberately slack cabling so nothing would snap under the strain. From there, the magnets are further cooled to 4.5 Kelvin using liquid helium. The final stretch, down to 1.9 Kelvin, requires a sophisticated pumping system that lowers the pressure on the boiling helium until it transitions into a superfluid state, a phase of matter where it flows with virtually no viscosity at all, dramatically improving its ability to carry heat away from the magnets. Serge Claudet, who led CERN's cryogenic operation team, described the milestone when the first section of the LHC reached this record cold back in 2007. After more than 10 years of designing, building, and testing each individual piece separately, the team finally had a chance to test an entire sector together for the first time. CERN describes the LHC's overall cryogenic system as the largest in the world, requiring 40,000 leak-tight pipe seals, around 40 megawatts of electricity, roughly 10 times what's needed to power a locomotive, and about 120 tons of helium, all just to hold those magnets at 1.9 Kelvin, colder than empty space itself, day after day, year after year. And this isn't a one-time achievement CERN is simply maintaining. The same basic approach is being extended even further. As part of an ongoing upgrade program aimed at boosting the collider's performance ahead of a planned return to operation around 2030, engineers have built a full-scale, above-ground test stand, essentially a working replica of new hardware. and have already begun chilling new niobium tin magnets down to that same 1.9 Kelvin benchmark, colder than outer space, to validate a new generation of more powerful beam-focusing magnets before they're ever installed underground. So even before we get to individual atoms, there's already a machine, built by human engineers, sitting underground in Europe, that permanently maintains a temperature colder than the vacuum of deep space, simply because the physics of superconductivity demanded it. And the LHC isn't even alone in this club. Modern quantum computers, the kind being developed by companies like IBM and Google, run into essentially the same problem for closely related reasons. Superconducting qubits, the building blocks of these machines, depend on extremely delicate quantum states that get destroyed almost instantly by ordinary thermal noise, the same random atomic jiggling that defines temperature everywhere else in this video. To keep that noise from wrecking the calculation, engineers cool these processes using devices called dilution refrigerators, which use a closed-loop mixture of two different helium isotopes to reach temperatures far colder than a standard liquid helium setup, which typically only manages around 4 Kelvin on its own. Many of today's leading quantum computers run at around 10 to 50 millikelvin, thousandths of a degree above absolute zero, with some state-of-the-art systems pushing down to 20 millikelvin or lower. All of it, again, colder than the roughly 2.7 Kelvin vacuum of deep space. IBM built what's reportedly the largest dilution refrigerator in the world, a device nicknamed GoldenEye, standing about 10 feet tall and 6 feet wide, designed to eventually support quantum systems with up to 1 million qubits. It can reach temperatures as low as 15 millikelvin, though it takes between 5 and 14 days of continuous cooling just to get there. Chris Spitzer, operations lead at the Advanced Quantum Testbed at Lawrence Berkeley National Laboratory, described the cooling hardware involved in similar systems as resembling golden chandeliers with cables running up and down, a strange, almost decorative image for machinery built to hold a temperature colder than anything found naturally, anywhere between here and the edge of the observable universe. Researchers keep pushing that number down further too. In early 2025, a team at Chalmers University of Technology in Sweden, working with the University of Maryland, unveiled a small, chip-sized quantum refrigerator, powered autonomously by nothing more than ambient heat, that can be added onto a standard dilution refrigerator, taking qubits that would normally bottom out around 50 millikelvin down to a new record of about 22 millikelvin instead. The cable that makes up the LHC's powerful electromagnets carries roughly 11,800 amperes of current, which is about as much current as flows through a small bolt of lightning, compared to the roughly 9 amperes drawn by an ordinary household toaster. For a cable no wider than a finger to carry that much current without simply melting, it has to be a superconductor, held at that extreme, space-beating cold, wrapped in layers of insulation, nested one inside another, almost like a matryoshka doll, each layer colder than the one before it, protecting the magnetic core at the center from the comparatively balmy temperatures of the tunnel around it. That's just the warm-up act, so to speak, for exactly how far human beings have actually managed to push the boundaries of cold. And it isn't only particle accelerators and quantum computers chasing that goal either. Deep underground at the Gran Sasso Laboratory in Italy, an entirely different kind of physics experiment called Quare, built to study the behavior of neutrinos, runs its own multi-stage cryostat down through a series of progressively colder stages, finally settling at a base temperature of around 10 millikelvin, cooling roughly 2,000 kilograms of hardware down to a point routinely unremarkably colder than deep space itself. It's a useful reminder that reaching temperatures colder than the vacuum of the universe isn't some rare, singular achievement performed once for a headline. It's something dozens of laboratories around the world now do routinely, as a simple prerequisite for getting their actual physics experiments to work at all. Before diving into exactly how cold these laboratory experiments actually got, it's worth understanding, at least in broad strokes, how scientists managed to cool a handful of atoms down this far in the first place, because the method itself is almost as remarkable as the resulting temperature. It generally happens in 2 stages. The first stage is called laser cooling, a technique significant enough to have earned its own Nobel Prize in Physics back in 1997, which works by aiming precisely tuned laser beams at a cloud of atoms in such a way that the atoms are gently, repeatedly nudged into slowing down every time they try to move, gradually draining their kinetic energy, and therefore their temperature, without ever touching them directly. But laser cooling alone can only get you so far. It becomes far less effective once the atoms are packed closely enough together, so a second stage, called evaporative cooling, takes over from there. Evaporative cooling actually works on the exact same basic principle as a cooling cup of tea, or as the human body cooling itself through sweat. If you can arrange for the most energetic particles in a system, the hottest ones, to selectively escape, they carry away more than their fair share of the total energy when they leave, which drags the average energy, and therefore the temperature, of everything left behind steadily downward. In these experiments, the atoms are first captured inside a magnetic trap, sometimes nicknamed a magnetic bottle, a carefully shaped magnetic field that confines the atomic cloud in empty space without the atoms ever touching any physical surface, since, as we mentioned earlier, no physical container could survive contact with matter this cold anyway. From there, researchers gradually and selectively let the most energetic atoms escape the trap, sometimes using radio frequency fields to nudge only the hottest atoms out, letting the calmer, colder atoms settle further and further toward the center, re-equilibrating after each round of escapes at a slightly lower overall temperature than before. Repeat that process enough times, patiently, carefully, and you can coax a cloud of ordinary atoms down into the nanokelvin range and beyond, right to the edge of what physics allows. The story begins in 1995, when researchers at the University of Colorado, Boulder, working closely alongside a separate team at MIT, led by physicist Wolfgang Ketterle, managed to cool a carefully contained cloud of atomic gas down below 1 microkelvin, 1/1,000,000th of a degree above absolute zero, a temperature so extreme it's genuinely difficult to picture in any everyday terms. At that temperature, something remarkable and entirely new happened. The individual atoms making up the gas stopped behaving as separate, independent particles bouncing around randomly and chaotically, the way gas molecules normally behave at any temperature we're familiar with, and instead began moving together in perfect, synchronized lockstep, forming an entirely new state of matter that came to be known as a Bose-Einstein condensate. It's sometimes described, somewhat poetically, as the atoms acting like a single, giant superatom, a unified, collective quantum entity, rather than a disorganized crowd of individual particles, each doing their own thing. This particular discovery turned out to be significant enough, scientifically, that it eventually earned Ketterle, along with his Boulder-based colleagues Eric Cornell and Carl Wieman, the Nobel Prize in Physics in 2001, 6 years after the original breakthrough. That 1995 discovery opened the floodgates for an entirely new kind of ongoing scientific competition. Exactly how much colder could researchers actually manage to push matter, now that they finally had a working, reliable method for getting this genuinely close to absolute zero in the first place? Over the years that followed, research groups scattered across the world became increasingly, remarkably skilled at reaching nanokelvin temperatures, billionths of a degree above absolute zero, with 3 nanokelvin standing for a time as the best recorded figure anyone had managed to achieve. Then, in 2003, Ketterle's team at MIT shattered that existing record entirely, cooling a carefully prepared cloud of sodium gas down to an astonishing 500 picokelvin, half of 1/10000000th of a degree above absolute zero, and in doing so, becoming the very first research team in history to successfully cool a gas below the 1 full nanokelvin threshold. At temperatures this genuinely extreme, ordinary physical containers become completely, uselessly impractical, because the atoms themselves would simply stick permanently to the inner walls of any solid container they came into contact with. And in any case, no known physical material could realistically survive being cooled to such an extreme temperature without some kind of structural failure. Instead, the atoms in these experiments have to be suspended entirely within carefully, precisely shaped magnetic fields, held in place by nothing more than invisible, carefully calibrated forces, floating completely free of any physical surface whatsoever. That particular record held firm for years, until 2018, when a dedicated research team working in Bremen, Germany, as part of a broader research collaboration known as Quantus, managed to push the boundary of achievable cold even further than anyone had managed before. Their overall approach was genuinely inventive and creative. Rather than relying purely on lasers and static magnetic fields the way earlier record-setting experiments largely had, they took a carefully prepared Bose-Einstein condensate made from rubidium atoms and dropped it down a specially built drop tower, a purpose-built structure standing 393 feet, or about 120 meters, tall, specifically designed to create a few brief, precious seconds of genuinely simulated weightlessness during the resulting fall. In that momentary freefall environment, using precisely controlled, carefully timed magnetic fields to further manage the condensate's behavior as it plummeted downward through the tower, the team achieved a genuinely staggering 38 picokelvin, just 38 trillionths of a single degree above absolute zero, and managed to successfully sustain that extraordinary temperature for roughly 2 full seconds before the drop itself came to an end. Their formal findings were eventually published in the respected journal Physical Review Letters on August 30, 2021, and the achievement is officially recognized by Guinness World Records as the single lowest artificial temperature ever measured anywhere by anyone using any method. Remarkably, the research team involved noted afterward that if the exact same basic technique could somehow be performed under genuine, sustained microgravity conditions, rather than relying on the brief handful of seconds provided naturally by a drop tower's short, limited fall, they believed the resulting ultra-cold condensate could theoretically be held stable and intact for as long as a full 17 seconds. Just sit with that particular number for a moment and compare it directly, side by side, with everything else we've carefully walked through up to this point in the video. The Boomerang Nebula, the coldest natural place ever found anywhere across the entire observable universe, sits at roughly 1 full Kelvin, 1 full degree above absolute zero. The laboratory record set in that German drop tower sits at 38 picokelvin, 38 trillionths of a single degree above absolute zero. That means the coldest place human beings have ever managed to deliberately create is something on the order of roughly 10 billion times colder than the coldest natural place we have ever managed to find anywhere among the stars, using our most powerful telescopes and most sophisticated instruments. That's a genuinely difficult gap to fully picture or hold in your mind all at once, so try imagining it this way instead. Picture the entire distance between ordinary, everyday room temperature and the Boomerang Nebula's frigid 1 Kelvin as a single, very long, very demanding journey. The additional distance separating that nebula's temperature from the picokelvin laboratory record achieved in Germany would dwarf that first journey almost completely by comparison, representing not simply a further leap along the exact same familiar road, but something closer to an entirely different scale of existence altogether, barely comparable using the same everyday numbers we're used to working with. And remarkably, it happened not out among the distant stars at all, but rather inside a dedicated research facility, using a tower built specifically and deliberately to let scientific equipment fall far enough to briefly fake, for just a few fleeting seconds at a time, the exact same weightlessness that spacecraft experience completely naturally, every single day, out in orbit around the Earth. This particular pursuit of ever colder temperatures certainly isn't finished yet, either. NASA operates its own dedicated research facility for precisely this kind of ongoing work, called the Cold Atom Laboratory, launched directly to the International Space Station, specifically so that scientists could study Bose-Einstein condensates under genuine, sustained microgravity conditions, rather than having to rely on the brief handful of seconds provided by a falling tower back on the surface of Earth. In an update released in 2022, NASA reported that the ground-based testbed used to prepare, test, and refine the Cold Atom Lab's actual flight hardware before launch had itself reached a temperature of 200 nanokelvin, 200 billionths of a degree above absolute zero, a milestone that Rob Thompson, the Cold Atom Laboratory's project scientist based at NASA's Jet Propulsion Laboratory, described quite plainly and directly at the time. It was, in his own words, official that the Cold Atom Lab's ground testbed was now the single coolest spot anywhere at NASA's Jet Propulsion Laboratory. sitting at exactly 200 nanokelvin, and that successfully achieving Bose-Einstein condensation in that particular piece of prototype hardware represented a crucial, necessary step forward for the overall mission as a whole. Aboard the actual space station itself, operating in the genuine, continuous, sustained microgravity of true orbit, NASA has stated publicly that interaction times and temperatures as low as 1 full picokelvin, 1/1,000,000th of a degree above absolute zero, should eventually be achievable through this ongoing research, a level of cold that, if and when it's finally reached, NASA itself describes as colder than absolutely anything else currently known to exist anywhere in nature, whether here on Earth or anywhere else in the observable universe. It's worth pausing to ask why any of this actually matters, beyond simply setting a new record for its own sake, because the pursuit of extreme cold isn't just an abstract competition. When atoms are cooled down close enough to absolute zero, their ordinary thermal motion, the random jiggling that defines temperature everywhere else, gets suppressed almost entirely, which allows their underlying quantum behavior to take over and become something scientists can actually work with and measure. That's the whole basis behind cold atom quantum sensing, a growing field that uses ultra-cold atoms to measure things like magnetic fields, gravitational forces, and the passage of time itself, with a level of precision that would be impossible using ordinary, warm matter. Modern atomic clocks, for instance, typically work by cooling a gas of atoms like cesium or rubidium down to near absolute zero using laser cooling, then holding them in place inside a three-dimensional grid of laser light called an optical lattice, where researchers measure the extraordinarily precise energy released as the atoms transition between specific quantum states. Researchers at GILA, a joint research institute run by the University of Colorado Boulder and the National Institute of Standards and Technology, trapped roughly 30,000 strontium atoms this way, cooled to less than 1/1,000,000th of a degree above absolute zero, and used quantum entanglement techniques to push the resulting clock's precision even further than ordinary methods would normally allow. Researchers Yang and Maya Miklos, part of the team behind that work, used a technique called quantum non-demolition measurement, which let them extract information about the atom's collective state without significantly disturbing them in the process, something like checking the temperature of a pot of soup without ever having to lift the lid. These kinds of ultra-precise cold atom sensors already have real, practical applications on the table: magnetic field measurement, gravitational sensing, navigation systems that could work even where GPS signals can't reach, and tests of some of the most fundamental constants and theories in all of physics. In 2025, researchers at the National Institute of Standards and Technology built a related device they called a Rydberg thermometer, cooling rubidium atoms with lasers and magnetic fields down to about 0.5 millikelvin, and using the atom's own quantum behavior to measure temperature directly, without needing the factory calibration ordinary thermometers require. NIST research scientist Chris Holloway explained why that particular breakthrough mattered for the atomic clocks described a moment ago. Atomic clocks are exceptionally sensitive to temperature changes, which can cause small errors in their measurements. We're hopeful this new technology could help make our atomic clocks even more accurate. That's ultimately the deeper reason NASA keeps funding research like the Cold Atom Lab, and the reason engineers in Germany kept lowering a cloud of atoms down a drop tower, and the reason a Dutch physicist spent decades chasing liquid helium more than a century ago. It was never simply about seeing how cold something could get, for its own sake, as an empty record to chase. It was about what becomes possible, scientifically, once you actually get there. It's worth pausing here, before we bring everything together, to actually sit with the full scale of everything we've just walked through, because it's easy to let numbers like these slide past, without really absorbing what they mean. We started this video at room temperature, a comfortable environment most people barely think about because it's simply the background condition of everyday life. From there, we dropped down to absolute zero, a floor that physics itself says can never actually be touched, only approached, forever, one smaller and smaller step at a time, according to a law first written down in 1912 and never once broken since. Along the way to that unreachable floor, we found that empty space itself isn't simply cold in the same casual sense that a winter morning is cold. It's cold because it's empty. because there's almost nothing there to carry warmth from one place to another, except for the slow, comparatively weak mechanism of radiation, leaving objects to drift toward whatever temperature the universe's own ancient, faded afterglow happens to settle them at, roughly 2.7 Kelvin, the leftover light of an explosion that happened nearly 14 billion years ago, first measured by accident in 1965, and then mapped with ever-increasing precision by COBE, WMAP, and Planck over the following 4 decades. Along the way, we also took a short detour across the rest of our own solar system and found that the record for coldest natural spot doesn't even belong to some distant nebula. It belongs to permanently shadowed craters on our own moon, just a few 100,000 miles away, colder even than the surface of Pluto despite Pluto sitting 40 times farther from the Sun. We found Uranus, oddly colder overall than Neptune, despite sitting closer to the Sun, simply because it radiates almost none of its own internal heat back out into space. We found Titan, wrapped in a thick, hazy atmosphere at nearly 180 degrees below 0 Celsius, where a small European lander named Huygens made the only landing humanity has ever achieved anywhere in the outer solar system, briefly transmitting data home from a world colder than anywhere on Earth has ever been. And running underneath all of these numbers, we found the man who gave us the scale to measure them with in the first place, William Thomson, Lord Kelvin, who in 1848 proposed the very idea of an absolute 0 point, a concept picked up decades later by Heike Kamerlingh Onnes in a Dutch laboratory, who first liquefied helium in 1908, discovered superconductivity in 1911, and in doing so, quietly laid the groundwork for machines like the Large Hadron Collider and today's quantum computers, both of which now sit, deliberately, at temperatures colder than deep space itself, right here on the surface of the Earth. We found a nebula, 5,000 light-years away, that somehow manages to sit colder than the universe surrounding it, purely by accident, purely as a side effect of a dying star violently blowing off its own outer layers fast enough and long enough to create a kind of natural refrigerator on a scale no laboratory on Earth could ever hope to physically replicate in terms of sheer size, even if human laboratories have gone dramatically further in terms of sheer, raw temperature. We found a space station orbiting a few 100 kilometers overhead, silently enduring temperature swings of nearly 500 degrees Fahrenheit across its own hull every 90 minutes, while the astronauts inside experience nothing more dramatic than a comfortable, climate-controlled room, thanks entirely to careful engineering, circulating ammonia, and a thermal control system most passengers on the station probably don't think about any more than most people think about their own home's furnace. We found 2 aging spacecraft, Voyager 1 and Voyager 2, quietly drifting billions of miles from home, kept alive not by any single dramatic act of heroism, but by the slow, patient, decades-long arithmetic of watts and heaters, as engineers on Earth carefully ration a shrinking, irreplaceable supply of warmth generated by decaying plutonium, buying a few more years of scientific data, one careful decision at a time. We found a telescope built specifically to be cold, deliberately, precisely, because being cold is the entire point, the very thing that allows it to see all the way back to the early universe without its own leftover warmth drowning out the faint infrared whispers of galaxies that formed billions of years ago. And then, at the very end of the journey, we found something that upends the entire premise most people would probably start with. If you simply ask them, cold, where would you expect to find the coldest place in existence? Most people, reasonably, would point outward, toward the stars, toward the vast emptiness between galaxies, toward some remote corner of the universe far from any warming star. And they'd be wrong, according to everything the actual evidence tells us. The coldest place we know of isn't out there at all. It's here. It's inside laboratories in Massachusetts and Germany, built by researchers using nothing more exotic than carefully shaped magnetic fields, precisely tuned lasers, and, in one particularly clever case, a 393-foot tower built specifically to let a cloud of atoms fall just long enough to briefly experience the same weightlessness that spacecraft experience naturally every day out in orbit. 10 billion times colder than the coldest place anyone has ever found simply by looking outward with a telescope. achieved not by searching further and further into the depths of space, but by looking more and more carefully at what's possible right here, on the ground, within reach of human hands. There's a kind of quiet irony sitting at the very center of this whole story, one that's worth calling out directly before we close things out. We tend to imagine deep space as the ultimate frontier of cold, the place where temperature reaches its natural extreme limit, simply because space is so vast, so dark, and so thoroughly empty of anything resembling warmth. And in most respects, that intuition holds up perfectly well. Deep space really is extraordinarily cold by any everyday human standard, sitting at roughly 2.7 Kelvin almost everywhere you'd care to measure it, colder than anything most of us will ever personally experience in our entire lives. But the single coldest point anyone has ever actually managed to measure, verify, and record wasn't handed to us by the universe at all. It was built, on purpose, through careful, deliberate human effort, using tools and methods refined over decades of dedicated research, chasing a theoretical limit that the third law of thermodynamics insists can never actually be reached, no matter how good our tools eventually become. So here we arrive, finally, at the full shape of the story we set out to tell, stretched across every scale we've covered today, from the birth of the universe nearly 14 billion years ago, all the way down to a laboratory drop tower in Bremen, Germany. Deep space itself, far from any star, settles at around 2.7 Kelvin, the lingering, faded afterglow of the Big Bang. Ancient light, stretched out over 13.8 billion years of continuous cosmic expansion until it cooled down to almost nothing at all, a whisper of warmth spread thin across the entire observable universe. The coldest natural object we've ever actually found, the Boomerang Nebula, manages to slip even below that cosmic baseline temperature, using the violent, sustained, high-speed outflow of its own dying central star as an accidental, unintentional refrigerator, dragging itself down to roughly 1 full degree above absolute zero, colder than the universe surrounding it. Spacecraft caught in low Earth orbit, meanwhile, don't experience a single, steady cold at all, but rather brutal, repeated whiplash between scorching, direct sunlight and total, absolute, freezing darkness, with nothing standing between astronauts and either extreme except carefully engineered heaters, external radiators, circulating ammonia coolant loops, and specially designed suits built to function as personal, wearable spacecraft in their own right. Out beyond the planets, spacecraft like Voyager and New Horizons survive on the slowly fading warmth of decaying plutonium, buying themselves a few more precious years of scientific function with every careful, difficult decision about which heater can still be justified and which one, reluctantly, has to be sacrificed to the cold. And high above all of that, a telescope named after a former NASA administrator deliberately makes itself colder than almost anything else humans have ever built and launched, specifically so that it can see clearly enough to look all the way back toward the very beginning of everything that exists. Closer to home, but no less strange, our own moon quietly holds the record for the coldest temperature ever directly measured anywhere in the solar system, tucked away in craters that haven't seen sunlight in longer than human civilization has existed. Colder, even than distant Pluto, despite sitting right on our own doorstep. Titan, wrapped in its thick orange haze out at Saturn, sits at a steady -180 degrees Celsius, a temperature a small wok-shaped European probe named Huygens touched down inside for just over an hour in January of 2005, in the only landing anyone from Earth has ever managed anywhere in the outer solar system. And underground, back on Earth, in a tunnel running beneath the border of France and Switzerland, engineers at CERN keep an entire 27-kilometer ring of magnets sitting at 1.9 Kelvin, colder than the vacuum of deep space itself, simply because superconductivity demands it, a demand first discovered in 1911 by a Dutch physicist chasing liquid helium in a laboratory that briefly earned the nickname the coldest place on Earth. Quantum computers, built by companies like IBM and Google today, chase that same basic principle down even further, into the tens of millikelvin, using refrigerators nicknamed things like GoldenEye that take more than a week just to finish cooling down. And none of it happened by accident. or purely for the sake of setting a record and moving on. Every one of these numbers traces back to a chain of very deliberate human decisions, stretching from Lord Kelvin sketching out the very idea of an absolute zero point in 1848, through Kamerlingh Onnes chasing liquid helium in Leiden 60 years later, through Penzias and Wilson cleaning pigeons out of an antenna in 1965, through Kobe, WMAP, and Planck sharpening that same faint signal into an ever-crisper baby picture of the universe, through engineers wiring a telescope named Spitzer to launch warm and cool itself gradually on the way to orbit, and finally, through modern researchers using that same accumulated century and a half of knowledge to build clocks accurate enough to test gravity itself, and sensors sensitive enough to navigate without satellites. Even distant curiosities like WISE 0855, a would-be star that never quite lit up, sitting a scant 7 light-years from home at a relatively mild 250 Kelvin, only make sense against the backdrop of everything colder that came before it in this story. A reminder that the universe offers up an entire spectrum of cold, stretching from merely frigid all the way down to the very edge of what physics permits. There's one final piece of this story worth sitting with before we close, and it takes us back to the very same man who gave us the temperature scale we've been using this entire time. Back in the 1850s, William Thomson, the same Lord Kelvin who proposed the absolute temperature scale in 1848, took the second law of thermodynamics and extrapolated it out to the scale of the entire universe, and arrived at an unsettling conclusion, that everything, given enough time, would inevitably wind down into what he called a state of universal rest and death. Other physicists of his era reached similar conclusions independently. Hermann von Helmholtz described a future in which the universe would be condemned to a state of eternal rest, and Rudolf Clausius described it as a state of unchanging death, once entropy, the measure of disorder in a system, finally reached its absolute maximum. Modern physicists still call this basic scenario the heat death of the universe, or the Big Freeze, and after the 1998 discovery that the universe's expansion is actually accelerating rather than slowing down, driven by the mysterious repulsive force called dark energy, it became the leading model for how everything eventually ends. Under this picture, roughly a couple of trillion years from now, distant galaxies will have drifted so far away that they'll no longer be visible from our own Milky Way at all. Around 100 trillion years from now, the last stars anywhere will finish forming and gradually burn out for good. Long after that, in what astronomers call the degenerate era, galaxies as we know them will effectively come apart, and eventually, virtually everything left will be locked away inside black holes, until even those finally, unimaginably slowly, evaporate. And at the very end of that almost incomprehensibly long process, the entire universe is expected to settle at a final temperature just barely above absolute zero, the same theoretical flaw we started this video with, the same line the third law of thermodynamics insists nothing can ever quite touch. In other words, the 2.7 Kelvin chill of deep space that we've spent this whole video exploring isn't simply a strange, isolated feature of the universe as it happens to exist right now. It's a preview. It's where the entire universe is slowly, patiently, relentlessly heading, over a timescale so vast that trillions of years barely register as a rounding error. The cold we've been describing this whole time, the Boomerang Nebula's record-setting 1 Kelvin, the Moon's permanently shadowed craters, the pico-Kelvin records set in laboratories in Massachusetts and Germany, isn't cold in spite of the universe's nature. It's cold because that's the direction everything, eventually, is going. Not every physicist treats that ending as a settled certainty worth adding, in the spirit of giving this story its full, honest shape. In the 1960s, the cosmologist David Laser pointed out that because the maximum possible entropy of an expanding universe actually grows even faster than its real, measured entropy does, a kind of gap opens up between the two, one that could, in principle, leave room for order, structure, and complexity to keep emerging indefinitely, rather than everything simply winding down towards stillness. More recent researchers have also pointed out that the long-term behavior of dark energy itself, the very force driving this whole scenario, isn't entirely settled either. which means the textbook ending could still shift as our understanding improves. But even accounting for that uncertainty, virtually every leading model still points in the same general direction, outward and colder, for a very, very long time to come. There's something almost humbling in that thought, and it's a genuinely fitting, quiet place to bring this whole long story back together, after everything we've covered. And through all of it, through every single stop on this journey, from the birth of the universe nearly 14 billion years ago to its almost unimaginably distant end, trillions of years from now, the deepest cold ever actually measured anywhere didn't come from any of those places at all. It came from right here, from human hands and human curiosity, from carefully shaped magnets and precisely tuned lasers, and a tower built specifically to let something fall freely for just a few fleeting seconds. Absolute zero remains exactly what it has always been, and exactly what it will presumably always continue to be, forever. A line that can be approached, endlessly, patiently, but never actually crossed. A hard limit, built directly into the fundamental laws of physics themselves. A wall at the far end of Zeno's old room that no one and nothing has ever actually managed to touch. But in the decades since Penzias and Wilson first stumbled onto that mysterious, persistent background static back in 1965, cleaning pigeons out of an antenna without realizing they were about to help confirm the origin of the universe, and in the decades since a dying star's violent outflow was found, almost accidentally, to be colder than the universe surrounding it, and in the years since a dedicated research team in Germany deliberately dropped a fragile cloud of atoms 393 feet down a purpose-built tower just to shave off a few more trillionths of a single degree, human beings have gotten astonishingly, remarkably close to that theoretical, unreachable limit, closer by a margin of roughly 10 billion times than the coldest known natural place anywhere among the stars. That's the real story of the unimaginable cold of deep space. Not simply how cold the universe happens to be able to get entirely on its own, drifting through emptiness for billions of years, but how far human curiosity, patience, and careful engineering have managed to push right up against the very edge of what the laws of physics actually allow, one careful, deliberate, hard-won degree at a time, in laboratories, on spacecraft, and underground tunnels, scattered across a single small, comparatively warm planet, orbiting a single, ordinary star.